right, introduction to IPv6. This video has been a long time coming. I'm actually going to make a whole video series on IPv6 at the request of a long time regular subscriber, DVD Gaunt 1. They asked the question, when am I going to make a video series on IPv6? And I said, you know what? Let me get that done. So I wrote up some notes here in a PDF. I know it's not a fancy PowerPoint presentation, but quite frankly, I suck at PowerPoint. Look, can't be good at everything. I suck at PowerPoint. I'm gonna work on that because it's more convenient to flip through the slides as I'm speaking and doing these presentations, these videos and stuff, because that's what they are, right? Presentations. So gonna start with this PDF. Gonna go into the basics of IPv6, and we're going to continue on this IPv6 path well up into configuring IPv6 IP addresses on Cisco equipment. I'm tapping my Cisco equipment right here. That's gonna be fun. I'll probably just do it in Packet Tracer because it's easier to demonstrate that way. And I want to say this: if IPv6 is intimidating to you, I totally understand, because the IPv6 address spaces are huge, and you might be wondering, how the hell am I going to subnet this? Or what are the protocols at play, and how do the protocols react to IPv6, etc., etc. But what I found fascinating with IPv6 is that it is a lot easier to use and even to subnet than IPv4. And you'll see why in a second. It's really fascinating, and there's a lot of benefits to using IPv6. Apparently there's some security benefits, some performance benefits, and a bunch of other benefits that I think that we will do well to utilize when we transition to IPv6, right? So before I even get into the content, I want to recommend this book right here. I was reading this book when I was studying for the CCNA. When I got to the IPv6 part, I found IPv6 to be so fascinating and interesting that I decided to buy a whole book on it. And I think the book I was reading recommended it, or was it the Portable Command Guide? One of those books recommended it, and I picked it up, and it was worth every penny. The reason why I found IPv6, or I find IPv6 to be so fascinating, is because, again, I was intimidated by IPv6 at first, and then I found, after using IPv4 and all of the routing protocols and going through all of that, I learned that IPv6 has so many benefits that built upon IPv4 that'll make our lives easier if we were just to transition to IPv6. Or at least that's how I look at it. Everybody is different in the IT world. People have their favorites. People, you know, have their annoyances with specific types of tools and software and stuff like that. But I actually think that we should transition to IPv6 ASAP, right? So get this book right here, and you won't be disappointed if you want to nerd out on this stuff. All right. So why IPv6? So many of you have already heard that we ran out of IPv4 address space, and sooner or later we're going to have to transition to IPv6. And depending on who you ask, we'll never have to transition to IPv6 because we can just NAT into eternity. Hey, it is what it is. People have their opinions on it. I think that eventually we're going to have to use IPv6. As a matter of fact, I think I know of 3 companies that are actually implementing IPv6. I believe Comcast is, Facebook, and Apple. I've seen an IPv6 address in the VPN feature that Apple is rolling out, right? It's still in beta, I believe, at the time of this recording. But I believe it uses IPv6 every now and again, or at least I thought I saw it. right? Scared the crap out of me one time because I'm not even gonna go down that rabbit hole, but so we're running out of IP address space, or we ran out of IPv4 address space, and we need to transition to IPv6. I believe we need to. It's time to move on, right? I'm getting tired of IPv4 anyway. Oops, try to scroll down. So IPv4 address assignments are administered and controlled by IANA, which stands for Internet Assigned Numbers Authority, which distributes these addresses to various RIRs, regional internet registries. So IANA controls all of the address spaces, including IPv4 and IPv6. You might be wondering about IPv5. IPv5, I believe, was never fully implemented. I believe it was used for an experiment or something like that. I forgot. I have to look that up. It's in this book. This book talks about it, which I highly, again, recommend that you get. It's really good book. So IANA distributes these addresses to various RIRs, and these RIRs assign addresses to various companies, right? Like ISPs and other companies, right? So there's 5 RIRs. There's AFRINIC, APNIC, ARIN, LACNIC, and RIPE-NCC. And on September 24th, just a little history for you. September 24th, 2015, ARIN announced that they've exhausted their pool of address space. On November 25th, 2019, RIPE-NCC announced that they've exhausted their address pool. And on August 21st, 2020, literally 2 years ago, LACNIC announced that they've exhausted their pool of address space. So as you see, we're all out of IPv4 addresses. We need to make our move to IPv6. We need to. I know a lot of people disagree with me, but yeah, we need to. Let's just go ahead and do it. You know, the devices that we're using is fully capable of using IPv6. We might as well just make the change. It's going to take some time, though. It's not going to happen overnight. It's kind of similar to how people want to make a full transition to electric vehicles, and I think that's going to take a very long time. You can't just get rid of the older technology and just, completely replace it with the newer technology at scale, right? At least not overnight. So what have we been doing to preserve this IPv4 address space? Well, we've been using Network Address Translation, NAT, and we're taking public IP addresses and translating them into private IP addresses, which are specified in the Request for Comments 1918. Can't do that forever. But some people apparently think that we can NAT into eternity and forever. I don't think so. I don't think that's even feasible. It's a waste of technology. Let's just go to IPv6, right? CIDR was also a temporary solution for reserving address space, as opposed to following classful rules with regard to divvying up the IPv4 address space and giving out whole Class A blocks and Class B, Class C. We can use classless rules and use /mask to section off different IP networks, different IP addresses, right? So we can take maybe, a Class A network, and then just slice off maybe, a /28 in that IP network and give it to a company, right? There's many different ways we can do that. I'm not gonna get into the details with that, but that was a way to reserve IPv4 address space, and apparently it's not enough, right? So back to the why of IPv6. Well, apparently better performance. I'm not really sure how yet. I haven't looked into that, and there's still more information that needs to be published on it. Maybe it's the larger address space. I don't know. Maybe that's what it is, and it allows for us to, transmit faster. I don't know. I have to look into that, right? So, the anatomy of IPv6. Going to be looking at the IPv6 address space as a whole. So, an IPv6 address has 128 bits. This address has 8 quartets. Some books call it quartets. Some books call it hextets. You're gonna see me use it interchangeably in this PDF right here. But this address has 8 quartets, which are essentially 4-digit spaces, like right here, right? These 4-digit spaces, right? And a colon separates each quartet, not a period like IPv4. So IPv4 uses a very small address space, like 32 bits, and IPv6 uses 128 bits, right? Kind of crazy. I thought it was insane. Like, what is this? This is an IP address. Like, why? Like, what are we doing? But you'll get used to it. So each digit in the quartet amounts to 4 bits, right? So 4, 4, 4, 4, right? 4 bits times 4 digits is 16 bits per quartet, and 16 bits times 8 quartets gives you 128 bits total for the whole address. Simple, straightforward math, right? So why is that important? It's very important that you know that, because moving forward, you're gonna have to do, you might not have to, but depending on how an ISP decides to assign your global routing prefix, you may or may not have to do a little bit of binary math here and there. But I wouldn't worry about that too much, not yet, because we have enough address space to assign these huge sections of subnets and stuff like that. Let's not even get into that right now, because that can get a little crazy. So as opposed to IPv4's 4 billion plus IP addresses, and this looks tiny. 4 billion is definitely not enough. Like 4 billion addresses in comparison to how many devices we have per person is just, it's nothing, right? Because I have, see how many devices I have. Got 1, 2, 3, 4, 5, 6, 7. I would say total in my house, I might have, I don't know, maybe over 20 devices that need IP addresses. So if you multiply that by every person, let's say every person on this planet ends up having internet and maybe 5 devices each, which is probably never gonna happen, but let's just say, and there's about 7-8 billion people on this planet. Multiply that by 5, you're gonna get a really large number of IP addresses, right? So this number right here is more than enough to satisfy, that number is ridiculous. I can't even say that number, but this number I think is enough to satisfy all of the devices in the universe and the next universe. Let me not even exaggerate like that, but it's a lot of IP addresses to have. So this is the amount of IPv6 addresses that exist, right? Compare that to the little measly 4 billion, and you see the magnitude of space IPv6 provides, right? So going deeper into the anatomy of an IPv6 address, Each IPv6 address consists of 3 parts: the global routing prefix, the subnet identifier, and the interface ID. So here's how an IP address looks, right? You see 8 quartets or hextets, whatever you want to call it. And yeah, 128 bits. And there you go. This is your IPv6 address, right? So normally global routing prefixes are usually given a /48 block, right? They're given in /48 blocks to enterprises and different companies, whatever, right? So when you have this /48, you can start to figure out how many subnets you have, right? So right here, you have the global routing prefix, and then now you have the subnet ID, which is 16 bits. So you have 16 subnet bits to work with. So 2 to the 16, what's 2 to the 16? I think that's 65,535. Let's check. What is 2 to the 16th power?
That would be 65,536.
Yeah. So I was off by 1. So 65,536 for your whole enterprise. Like it's crazy, right? So you have all of these subnet bits to work with, and then you have the interface ID right here, which is 64 bits. And most of the time when you're configuring IPv6 address, I know I'm skipping ahead, you'll set up the prefix, you'll write out the prefix, and you can use a /64, and then you can set it so that the router automatically assigns this interface ID. But I'm hopping ahead. Or you can manually configure the whole address with the prefix. Getting a little too excited. So let's go over this again. So the IPv6 address has 3 distinct parts. It has the global routing prefix, which is 48 bits, usually, if the ISP is not trying to be difficult. Then you have the subnet ID, which is 16 bits, gives you more than enough space or gives you more than enough subnets to work with, pretty much forever. And then you have the 64-bit interface ID. And again, there's many different ways to get this, not many different ways, but there's a few ways that you can get this interface ID, right? Now, the next very basic thing that you want to learn about IPv6 addresses is abbreviation of these addresses and expanding these addresses. Quite frankly, look at this. It's a big ass address. Nobody wants to type all of that out or write all of that out all of the time. So there's a way to contract that, to abbreviate it. And there's 2 rules that you can use. And then you can combine those 2 rules to form a 3rd rule, if you will. And those 2 rules are: you omit leading zeros and you omit all zeros, right? So I don't want to say omit all zeros because you technically can't do that, but you'll omit all 0 hextets. But we'll go into that, right? So rule number 1: omit leading zeros. So we have this example right here, right? I believe it's the above number, yeah, right? And we want to shorten this address so that we don't have to break our wrist writing this out or typing it out, right? Typing the whole thing. So we can remove all leading zeros and rewrite the address like this. See the difference? Huge difference, right? So what we essentially did was we leave these zeros alone, right? There's no leading zeros here. We see a leading zero right here. We omit that and rewrite it as DB8. We see a leading zero right here. We omit this and rewrite it as 100. We see 2 leading zeros here. Omit that and we have 20. And then we have 3 leading zeros here, omit that, and we have 3. No leading zeros here. We have 3 leading zeros here, omit that, and then we have 1 0 here. 3 little leading zeros here, omit it, and then we have 1. Simple as that. You don't need to bust any brain cells thinking about this, right? And eventually it becomes second nature. Also, you typically write these IPv6 addresses in lowercase. Wherever there's letters, it's lowercase, I believe. I believe it's lowercase. Some people write it with caps, but I think the standard is to write it in lowercase, right? Now we're getting a little technical. Here. So again, remove all leading zeros and rewrite the address like this. And then for the quartet with all zeros, you can put 1 0, right? Which is essentially kind of like removing all leading zeros, right? So let's take another example. So we have this right here, right? Let's remove the leading zeros. There's no leading zeros here, but there's a leading zero right here. So we rewrite it as DB8. We have 3 leading zeros here, omit it, and we have 0. 2 leading zeros, omit it, and we have 20. No leading zeros here, so we just write the whole thing, right? Leave that alone. 1 leading zero right here, omit and rewrite. 1 leading zero here, omit and rewrite. 3 leading zeros here, omit and rewrite. Now it's much shorter, right? Now, here's something that you need to remember. Never omit trailing zeros because, first of all, that's wrong. You never want to do that at all. And secondly, if you do, we just to use our imagination, if you do, it will create issues for you and others when trying to expand the IPv6 address. So there might be some circumstances, I don't know what circumstance, but there might be some circumstances where you need to expand the address. You might need to know the whole address. And if you have this example, right? So you have this, and you just start omitting the trailing zeros, right? You just start omitting these zeros. What you're gonna end up doing is screwing yourself over. You rewrite it like this, you rewrite it like that, and then somebody else comes along, maybe you or a colleague comes along, and by the way, this is wrong. I want to emphasize that is wrong. But when you try to expand it, look what happens. You get this, not this. Because remember, the original address that you were trying to abbreviate was this. You ended up getting this. Somebody comes behind you and wants to expand the IPv6 address for some reason, and they'll do it. They'll follow the correct way of doing it, but then they'll get the wrong IPv6 address. So never omit trailing zeros. That's wrong. Don't ever do that. Trailing zeros, these are trailing zeros. Like, don't even think about that at all, right? Just emphasizing and pointing that out because there might be some situations where you might get confused and you might think that that's a good way to do it or whatever. There's some interesting things that we all do sometimes, but don't do that, right? So next, let's see. Now when you want to expand, where did I leave off? Okay, so going back to expanding it the right way, right? So we contracted it down to this, right? This is where we left off. Doing it the correct way. All we must do is add zeros where appropriate to get the correct number, right? Which is this up here, right? So all we did was omit the leading zeros, and we got this. I'm looking at the wrong example. But if we want to expand, like say we want to expand this, All we do is add zeros where appropriate, and then we're good to go, right? I skipped it. I probably skipped over it. Or as a typo somewhere, I got lost somewhere. But yeah, all these IPv6 numbers. So again, if you want to expand this right here, you just add the zeros where appropriate, 0 in front of DB8. You add the 3 zeros here, 2 zeros in front, leave this as is, 1 0 in front, 1 0 in front, 3 zeros here, and you're good to go, right? So remember, the IPv6 address is 128 bits in total, so there's never any guesswork involved with the placement of the zeros. So you always know that if you see an abbreviated address like this and you want to expand it, you know that you just add a 0 here, right? And it will complete the hex tag or the quartet. You know that 3 zeros belong in front of this 0. It'll complete the quartet. You know that 2 zeros belong in front of 20. It'll complete the quartet. This is already completed. Leave that alone. Add 1 0 here, 1 0 here, and 3 zeros there. And you complete all of those respective quartets. And you're good to go, right? So the next rule is to omit all zeros hextets, right? Which is just another word for the quartets. Depending on which resource you use or where you're reading it, reading a question or whatever, you might refer to it as a quartet or a hextet or maybe something else, but they're all pointing to the same thing, which are these 4 digits right here, right? So let's go to the next one. All right, so say you have this example right here, right? You have this example right here, and it says omit all zeros hextets. So essentially, what you want to do here is we're gonna pretend like we don't know the first rule, right? And we're gonna abbreviate this this IPv6 address. We see 3 hextets of contiguous all zeros in all of the hextets, right? So what we could do here is just put a double colon right there, right? So when you have an IPv6 address, such as the one above, you can utilize the double colon to represent 2 or more contiguous hextets of all zeros. So you can rewrite the above example as this number right here, this IPv6 address right here, right? This double colon replaced these contiguous hextets of all zeros. Key here is that you can only use it one time, right? So if you had a number that had, I don't know, these 3 hextets right here, and then these 3 hextets right here, that's all zeros, and then you have maybe these are all zeros also. You can only put 1 double colon, and I guess you can put it wherever you want, but you can only use it one time. So you could either put it here, or you could have put it at the end, right? Let's just, again, pretend like this is a 0. Put it at the end, but you can't use both of them 2 times. I should have probably included that as well, right? So we have this as the abbreviation, and you can expand by adding the zeros where appropriate, again, right? First, add the necessary zeros where the double colon is, and we know that there are a total of 8 hextets in an IPv6 address. So there's no guesswork here. We know that there's 8 hextets in every address, and we can see visibly here that there's 1, 2, 3, 4, 5. So all we do is just fill in these double colons with these 3 hextets or quartets of all zeros. Simple and straightforward, right? Straightforward. Now, combining both rules together, we can abbreviate these addresses even further. This is the complete way. right? You ideally, again, you want to be using both rules at the same time so that you can get a complete abbreviated address. It'll save you the pain of writing these long addresses out, right? So here we go. We have this example right here. Again, I believe it's the same example as above. Yep. So when we combine both rules, right, omit leading zeros and omit all zeros hextets, we get this number right here. Look how short that is. Look how beautiful that is. That is so much shorter, so much more condensed, easier to read, easier to write, and it's just so much better, especially when you start seeing IPv6 addresses in routing tables. You don't want to see all of this. You don't want to see all of this. You want to see this. That is a good thing to see, because this, seeing all of this, it can really jack you up, right? Now, if there aren't any contiguous hextets of all zeros and they're all numbers, then I feel sorry for you, right? All numbers and letters, I feel sorry for you. So this is the fully abbreviated version, right? Abbreviated version. And then we have a nice condensed address, right? So we remove the leading zeros as well as use a double colon to represent the three contiguous hextets of zeros. When we expand this address, we're gonna get this address again, right? So that's pretty much that, right? We added the leading zero to BB8. We filled in these contiguous hextets of all zeros, and we know that because we got the double colon right here, and we also know that there's 1, 2, 3, 4, 5 hextets. In every IPv6 address, we need 8 total, so we simply fill that in with these zeros, right? We leave 1, 2, 3, 4 alone. We add 3 leading zeros to this zero. We add 3 leading zeros to that one right here, and then we have this example again, right? So that is some basics, some introductions to IPv6. I highly recommend you get this book here, IPv6 Fundamentals by Rick Graziani, and start reading it up if you need like more supplemental reading, or if you want to dig more into the history of IPv6. And yeah, that's pretty much it. I hope you liked this video. I hope it was informative. I hope it helped you to understand the basics of IPv6, what an IPv6 address looks like. This is important right here, right? Global routing prefix, subnet ID, interface ID, and it's very easy to subnet an IPv6 address. It's really easy. You want to see how easy it is? I'm gonna do it right here, right now. All you have to do is you can increment this number right there. You can literally, that's your subnet. So your subnet would be this global routing prefix right here, and then you can just add 1 right there, and that's your subnet. And then you can obviously, however you choose to calculate the interface ID, use that method, and that's it. That's the subnetting for IPv6, but we're gonna get more into that in another video. But if you enjoyed this video, there's more videos to come with regard to IPv6, and we'll get a little bit more technical with that. And thank you for watching. I will talk to you guys next time. Peace.